All right. The final part of applications of Laplace transforms involves just a very important extension or the direction of state variables. And I'm going to talk about this first with pretty much how it is presented in the text, which is really kind of concise. And you will, especially those of you who are double E's, you will be exposed to state variables quite a bit. You get into mechanical engineering, um, and probably anything, an offshoot of mechanical like aero or any of that is going to be, you're going to encounter state variables quite a bit. In the double E side of things, control systems are really all about state variables. They just depend on your understanding of state variables. So we've had a simple diagram before where we had a linear system. We've been talking about it. Um, that is, has an input of something and an h of x, right? We've talked about this maybe in this form. Let's see if we can get the pointer going here. And we've kind of talked about it in this way where we've had, right, our h of s. We just got done talking about it this way. And y of s is our output, our response to x of s as an input. Okay, and now we're talking about this, a larger system with a whole lot of inputs, right, all along this side, just gobs of them here, and a whole lot of outputs, right? And the output is still y, but suddenly the input label is called z, and in a minute we're going to see that the state variables are identified as x. That used to be our inputs. So just hang a little loose because you'll get some definitions. So I'm pointing this out to say what you're about to see with state variables is highly related to Laplace and to transfer functions and transforms and such. Um, but just don't get confused by this switch because z is substituted as an input because we're going to start using x as a state variable. And as it says here, a state variable, it's a physical property that characterizes the state of a system, regardless of how the system got to that state. Okay, so state variables could be things like temperature, they could be pressure, they could be current, they could be magnetic fields, they could be other force fields, applied stresses. They just describe the state of the system, and it's not a function of how you got to that state, right? The set of equations are going to try to describe or model that process. All right. So here is a commonly occurring thing. You can barely see the dot here, but there is one. And the point of that dot is to say, it took it away on me. The point of that dot, right, is to say, is to say that that's the derivative, right? It's the differential. It's the differential of x. And what is this equation expressing? It's expressing the differential of x. X is a state variable. It's a state variable. The differential of that state variable is equal to a constant times the state variable plus a constant times the input. Okay? Now that's interesting. The differential action, so the rate of change function of a state variable can be expressed as the sum of constants times the variable itself plus constants times the input. All right, that's what's being expressed there. And the reason these are bold is because we have z as a vector, okay, and x is a vector. There are a lot of inputs, 1 through m, and there are many state variables, like 1 through n of them, okay? So the first thing that gets stated then to clarify this is that x dot, right, is x dot is the state vector representation of n state vectors. Okay, so, and this next piece will be a little confusing. I'm actually a little surprised that's how they represented it, but it will come clear because they then say this x dot, the authors do, is a vector of differentials of each of the state variables. Okay, now this vector here doesn't look equal to this vector here to me. This one is the state variables themselves, and this is the differential of those variables. Okay, but this one here is the one that we want to pay attention to. I'm not sure what they're expressing there, so I just caution you don't get too tangled up in that. A vector of differentials is exactly this run right here. Okay? Now, the input is a vector of inputs, and there are m of them. So notice the subscripts chosen are different because there can be m inputs, there can be n state variables. That might be more than the m inputs, it might be less, could be a lot less. It's just not the same number. And as a final thing, there are p outputs. Okay? So the complete description is just this. Here's the description of how the states go. The states proceed, I'll just say. All right? And this is the output equation. And all of this is matrix because matrix representation because we have multiple inputs, multiple outputs, and multiple state variables. So the output equation, it's a vector, is a constant times the state variables, not the differential of the state variables, just the state variables, and a constant times the input z. Okay? And so you end up with that vector having p outputs, all right? So a lot of things going on here. Now, I want to take a minute to maybe describe this in another way or in a close way. Because again, we're so used to seeing x as an input, and that's suddenly that changed. And why is that? Well, let's say we have this dynamic system here. Okay, this is our system. And the system is described by a set of state variables x. So this is a bold x, right? It's a vector, right, of all the x1s through xn. Okay, and that describes what goes on in this system. The x's do. Not the differentials, nothing else, just the x's do. Okay, so the system inside here, and obviously what we're going to want to be doing from here forward is describing this system which can be described or specified by a set of state variables. Okay? Now differentials, the variables themselves. And this is going to produce a y output, and it will be moved by or forced by a z input. Okay? Now there may be initial conditions on this, right? And that would be another way in which this gets set. Initial conditions, I've drawn an arrow going in. They are not inputs, they are initial conditions, the values on capacitors, the pre-bending of a piece of metal, or the stress of that, or the initial temperature of a chamber. I don't know. All right. So that's that. Now before I leave it, what I want to say is this: that you may have gotten at some point out of math in dealing with differential equations and stuff, but you need to recall that the input, or that a differential of x, right, the differential can be expressed as the sum of a1 times x1, and I'm going to delineate some subscripts here, allowing that there's a vector of many state variables. But we may have forgotten this, that it can really be written as a1 times x1 plus a2, right, times x2 plus a3 times x3 plus, and then you just get on to the various inputs, right? b1 times z1 plus b2 times z2 plus, and on you go through the end of those. Okay? And each of these in the set, right, there can be down to xn, can be written as what? Now we need an A1. Oh, so we better put an additional subscript here, right? This is the first A that manages x1, relates x1 to x1 derivative. So now there'll be the nth A n1, all managing x1, right? So this is going on all down here. x1 plays a role, multiplied by a constant, plays a role in all of these differentials, all n of them, right? And x1 then, in each case, is multiplied by a different coefficient. And so here we go. We'll now need, oh, this coefficient must have been, it relates 2 to 2, but it relates 2 back to differential number 1. And here we've got differential number n with variable number 2, all right, plus differential number n against variable number 3. That means this must have been differential number 1, state variable 1, as related by state variable 3. Okay, so this is relating what? The state variable differential to one of the other state variables, right? And so the whole matrix fills out. So you see here, you're going to end up with this as a vector is equal to some large vector A, which is a matrix now, right? That's a matrix times the vector of x, right? So this guy is a vector. This is a vector. This guy is a matrix. right? And what is that going to be? Oh, that matrix, we got n state variables, and it's relating n state variables to n state differentials. So this must be an n, an n by n matrix. Okay? Now the same thing is going to go on with B. I think we understand that. So this can go on with B. And what will this be now? We have input Z1, and it's related to the nth state variable. So this must have been B11, right? This would have been Bn2 times the second, input. So this would have been 1, 2 times the second input, and so on. All right, so this is what's really going on when this is being expressed. This was the same equation the authors used, but I'm just trying to open it up a little bit so you get a little more feel. So this is going to be a vector, right, of size m. This is a 1 by m vector, and this is a 1 by n vector, and so B must be what? B must be an n by m matrix. Okay? But the interesting thing is, again, to remind you, from differential equations, you need to remember that. Where is my pen? Where did my pen go? Yeah, you need to remember that this is true. That the derivative of a variable can be expressed as a constant times the variable plus a constant times the input. Okay, an important thing, and it's just expanded and enlarged in two directions here to get all of this going about state variables. All right, so let's then tidy up the language. I think that's our next step. If we try to take the Laplace of this, right, the left side, remember this is now, what is this? So we'll try to take our left side here, and remember this is what? This is the Laplace of x, the differential of x. Okay, constant times the Laplace transform of x is straightforward. That's a constant times it plus a constant times the transform of the input. So this is a fairly simple equation we got here. We like that. So now we've got our state variables and our state variable matrices. We got this all packaged, and all we had to do was express this simple s term, s multiplier right there to take the derivative. So now if we do our shuffle and change here to get the x's on one side. Nice thing here is this derivative. This derivative just became a function of x of s itself. So we come over here and look, we just get now a new matrix times x of s equals b times z of s. Okay, so this is a form, and these are all constants. The identity matrix, well, times s, and then the constant A matrix. Right, so this is looking like we could solve this, right? X is equal to BZS over this thing, or other forms that we might want to do. Right? So here we are. We just take the inverse. We know how to do inverses of matrices. We'll have to do that if we're taking this composite matrix of S times the identity minus A. Right, so manufacturer take the inverse of that, and quickly then we can solve for x of s. Similar thing can go on with y. We want to bring y of s along, although it was easier just to begin with. Now if we've got x of s, right, that can go right in here if need be. And z we know because it's the forcing function. All right, so now what about a transfer function? Now we're into a place where if we go back to our big old box, we want to know what's the transfer function of this thing, even though we have state variables inside. All right, now we just remember we had a name change here, so z on the input, y on the output. All right, and h of s then is just the ratio of those two. The transfer function h of s is y divided by the input. Interesting. But we also know that the transfer function, because we could go back up in here and plug our x of s into here. Look, we've got c times x of s. Oh, all of this thing goes right in here. Well, here it is, down here. Right, piece of cake. Plus d, we factored out the z, and it goes over there. So we're in good shape with that. Okay, and now we've got transfer functions for a system of state variables. All right, so let me just summarize then. We can express our transfer function here finally as this. And let's, the transfer function is really the function that relates the transfer function is really what relates the input to the output. No great statement there. But this thing called D, this feed-forward matrix, once we've formed the ratio of y over z, that transfer, that D is that feed-forward matrix. This is true when D equals 0, this feed-forward matrix, which is quite commonly the case. Okay, I mean, what is that doing? That's relating the input directly to the output. In other words, it's not engaging the state variables at all. So that's not a typical case. So not a problem here creating this simplified version right here. All right, and we like that. It's constant matrix, constant matrix, constant matrix. The identity matrix, once you know the size, and that's what, an n by n. And then we take the inverse. All right. So let me just summarize then with applying the state variable method step by step. Very similar to what we've already seen. The real trick is selecting the state variables. For circuits, it's typically inductor current and capacitor voltage. Why those? Because they have differential relationships. They have derivative-based relationships. State variables around a resistor. I mean, we've done enough mesh circuits in that mesh analysis of resistive circuits to know that there isn't a differential involved, and those are kind of straightforward. You get a system of equations, but you can solve them straight away. So ours are going to involve, especially involved circuits where there's an inductor and or a capacitor. All right, in mechanical systems, you're just looking for things that likewise relate to variables, like in our case, current and voltage, relate to variables by a differential form. And that's a way of helping you select what are the state variables. For us, we use really basic stuff, blocking and tackling, Kirchhoff's voltage law, Kirchhoff's current law. Why is that? Well, we want that system of equations. We want that set of equations. Only now they're going to have, remember, they're going to be this x bar x dot is equal to ax plus bz, right? So you're going to be looking to form equations that relate to this derivative term. And then you obtain the output equation and put the final result in state space representation, right? And we're going to be talking about that. Let's take a look at a couple of problems. Problem 610. This is a simple enough circuit, and we just want to get the idea here. I'm going to tell you ahead, these are obvious. We're going to follow the advice of the text, which is look to the inductors and capacitors for your state variables. Those have been identified here. I is the current in the inductor, V the voltage across the capacitor. And just to remember, the voltage across the inductor is L di dt. Whoops. Okay, so we can write that as V equals L I dot. Okay, and then I dot, so this is V of the inductor here, so that I dot is equal to 1 over L times the voltage across it, which is what, our V minus V0. Whoops, V minus V0. All right, then the voltage across the capacitor. So this looks like it might be a useful state variable. It's probably only one of only two, and we're going to need two here. So let's also try then the capacitor, right? The capacitor, the current, the current in the capacitor. So I of the capacitor is C dV dt. All right, so we can write this very easily as what? The V of the capacitor, or V in this case, I'll get rid of this since it's already labeled in the diagram. So V dot is equal to 1 over C times I of the capacitor. Okay, and let's just do that. So the current up here entering the node will be V source minus V, that's our state variable, over R1. All right, and then that is minus I. Okay, so that's the current in the capacitor. 1 over C times that is the derivative of the voltage with respect to time. All right, so that's our basic starting point. We've kind of identified our state variables, I and V, and the equations that relate them. And notice very nicely, we've got V out in one equation. So let's have that. We're probably going to need that at some point. V out is equal to I R2. And that's our output equation. Okay, so that's going to be an important one. That's going to be one of our basic equations, and that is going to be one. All right, let's get those in the form. Remember now, we're headed for this form in terms of our variables. V dot, I dot, right, is equal to what? Our A matrix times our state variables, V and I, plus a B matrix times our input, right, our input equation, which is, or our input variable, which is Vs. Okay, we're going to want this. We're also going to want an output equation. So we're also going to need the second one. So casting this in terms of our state variables, not the x and y and z in the generalized presentation, that's all I'm doing here is getting us set. So we know what it is we're going to go for. We're going to have to find this A matrix and the B matrix, or probably more like a vector in our case. But so our output equation, V0, right, we've got that already, it looks like. That's our I. Actually, I should cast it as R2 times I, right? So that's kind of the form. Let's see, the form of this is what? It's V0 is equal to C times the state variables, right? C times our VI plus D times our input, VS, right? So we're kind of already done here. We already know our V out. Our C matrix is just this, what? 0 R2, right? That's our C times VI. Okay, so we're done with that part of the state variable model. All we got to do now is basically get our A and B matrices. All right, so we're going to do that right away. We got our equations, so let's clean this up and pull it together. And that pretty much amounts to writing this in a neat fashion. So we've got our V dot and our I dot. And that's going to be equal to, what is it for A? So let's look down here with our V dot equation. I'm down here looking at this, trying to get this factored. So let me take this maybe another step right here. I will have, what, 1 over C R1 times VS minus V minus I over C. Okay, where this and this are state variables, and this is the source, right? That's going to be our B term. So we can go up here into and start filling in our A matrix now, right? We've got, oh wait, I got to be careful how I do this. This is 1 over R1C times this, all right? So let's see, our A matrix, I'm going to go up here and just fill it in. So the VS term will leave for that's part of the B matrix. So I'm going to have minus 1 over R1C, right? And that'll be times, just to kind of keep it visualized, I'll just fill this out ahead of time. So I got V and I. You may have your own techniques for writing these matrix equations, but that's up to you. That's how I do it. I kind of fill in the structure and then start to go after the details, right? So now I've got that term in. The second part of the V dot equation is minus 1 over C times I, right? So where am I? This is minus 1 over C, right? And now I take my I equation, and it looks like this is what? 1 over L times V. I don't think I need to expand that anymore. So it's 1 over L times V. That would give us that. And then the I dot is minus V0, but V0 is what? That's R2 times I, right? So it's 1 over L. So that's going to be our minus, let's see, I is, so that's going to be minus, V0 is R2I, so it's going to be minus R2 over L. Got to be this. All right. Now we just pursue, oh, well, we can add our B term in here. The B, so the B, we'll just set that up as what? That'll be a vector here. That will be, there's no contribution by the term V, and there's an R2 times this same vector then, the VI vector. Okay, so that's our state model, right? Here's the two pieces. This term right here is our output equation, and this whole thing right here is our state variable equation. All right, so that's the model. Now if we want to find the transfer function, right, let me just pursue this then. We know that the transfer function, because all of this got derived, and we could do the same thing, but that derivation was done very well in the text. It's C, and we have a C here, times S times the identity matrix minus A, and then take the inverse of that times B, okay? And all of this would be 0 if we didn't have something up here going on, but we do have a C. All right, so let's form this first. Obviously, the identity matrix is ones on the forward diagonal. All right, so that's going to be simply S and then 0 and 0. So we're going to have S something here. So we better plug in our values. I'm going to do my thing of filling out forms. So the C1 is what? 0, and R2 is 2, so that's going to be 0, 2. And then the one on the back end is simply 2 and 0, right? What is that? That's, yeah, that'll be 2 and 0. Okay, now what's up in between here? I think we're going to have, if we plug in our values of 1 over R1C, R1 is 1, C is a half, so that's a 2, and it's minus 2, so this is going to be minus A, so this is going to be plus 2. And up in the right-hand corner, we've got minus 1 over C, so that looks like a minus 2. So that'll be plus 2, right? And down in the lower left here, we've got 1 over L, and L is 0.2, so that looks like 5, and that will be minus 5, right? So minus 5. And in the lower right corner, we've got R2, which is 2 over L, which is 0.2, so that looks like it's probably going to be 10. And as a minus 10, and then the sign is inverted, so that's going to be plus 10. Okay, so that's our S times the identity minus A. We now have to take the inverse of that, so let's not forget about that. This is our transfer function. Okay, and I'm going to let you all worry about taking inverses. Okay, you'll have to go look at that. You'll find the determinant and all of that stuff, but I'm gonna speed it along here and just fill this. Right, we just do 0, 2. I don't do a lot of talking during this, and we reverse these two, so S plus 10. Change the sign on the negative diagonal, so this will be minus 2, 5, and S plus 2. 2 and 0, and this is all over the determinant, which is the square of those, the product of those two. Right, minus, so that'll be plus 10. All right, and the top, we can have 0 and 2, so that'll be 10. 0 times this is going to be 0. 2 times that is 10. And then 0 times 2 is 0. And 2 times this, so this will be 2 times S plus 2. Right, but that's with 2 and 0. right? So all of that is just going to amount to what? 10 times 2. So this whole thing is going to become 20. The bottom will be, it looks like by inspection, s squared plus 12s plus 20 plus 10 is 30. Okay, and I think, let's see what we have here. Yeah, that's the transfer function indicated. So that's how it's done. Obviously, things get a little messier, not so much writing the state variable model, but getting this inverse. The more state variables you have, right, inverses, these things become more and more of a challenge. At the level of 2 and 3 state variables that we'll be working at, it still stays manageable. All right, we're going to try another one. Problem 12. So here is a given differential equation. So I think just kind of to show that this is like solutions to differential equations, we can just go ahead with this. So we have our 3 state variables, right? We ought to be able to say, look, there's a first, second, and third derivative, right? So we'll say that y is one state variable, right? And let me maybe put it in terms of our usual x terms and that sort of thing. So what have we got here? We've got, I'm just going to make this statement, y of t is x1 of t, right? So that's going to be one of our state variables. Then y prime is, I'm going to call x2 of t is equal to x1 dot of t, right? So we're beginning to see our state variables are now going to be x1, x2, and x3, or they're going to be the various derivatives of y. So y double dot of t, to speed this up, will be x1 double dot, and we're going to call that x2 dot, right? And right, so x2 dot, and we'll label that as our x3, maybe another state variable. Okay, so our y triple dot of t is going to be equal to the first derivative of x dot, the first derivative of x3. Right, so if we want to line them up in the standard fashion, it might be something like this. Our x1 dot, x2 dot, x3 dot. So I'm just looking at the form of the text here, right? We're really talking about, right, what are our state variable equations. So we're going to have y dot, y double dot, y triple dot. Okay, just a reassignment. So this will be, here's going to be my A matrix, and what's going to be over here? X1, X2, X3. Right, and we can then just fill this out from the equation. Right, so what have we got? The first, okay, we can take all this directly from the equation. In fact, what's really happening here is we've already got two parts of this by defining the state variable. So really all we're going to do is take this equation and look at it this way. Y triple dot is equal to what? The output z minus 5y minus 20 y dot minus 18 y double dot. Okay, so I can fill out the whole bottom line of this thing right here quite easily, right? Starting with minus 5 minus 20 minus 18. Okay, and then the only thing that's missing is to add to it, right? We can have a plus z. Okay? All right, now let's go fill in the other equations. Well, they're over here. Look, our y dot equation, where is that? Our y dot equation is right here, and our y double dot equation is right there. So y dot is equal to x2. That's all we got to say. So we'll just come back. Where's my pen here? Whoops. X2 is going to be 0, 1, 0. Y double dot is equal to x3, so that's going to be 0, 0, 1. And there are no z terms involved there, so there's our A, right? In terms of the model, this is our A, this is our B, and what about C? Z is pretty much equal to Z, right? So the output in this case, I'm sorry, the input, the input, well, the contribution from Z is just 1, it's itself, right? So I'm sorry with this is not right. So what we want here is, whoops, this is not true. All we want to do is add the final term, which is this equation, right? So that y is equal to simply x1 of t. So that's going to be what? Our 1, 0, 0 times x1, x2, x3, and the d term is 0. Okay? So that is our, that's the state variable representation of a differential equation of multiple orders. So in essence, this is going to be another way of solving that basic math problem, irrespective of whether the system is electrical, mechanical, civil, or whatever. And there we have it. Okay, so a few words, I guess, about network stability that I always found useful because it allows you to just observe the transfer function and get some insight into how stable is the network, or how stable is the system described by that transfer function. So certainly the simple idea, the simple expression of it is, if I take the impulse response and take the limit as time approaches infinity, will that system have a finite response? In other words, if I take a system and I punch it, will it eventually settle into a finite response? Maybe it takes off, in a far out direction at first, but will it come back and settle back to a finite response? Or if I punch it, will it keep on floating out and just, go off? All right, so that's the basic test. So if we have the transfer function expressed as some numerator over some denominator, and we've been through this before, right? We've been through this before, and we know that the real requirement here is that the numerator has to have a lesser degree than the denominator, right? And that being the case, we can simplify, or we can simply express the transfer function as a numerator, which could be factored into a bunch of s plus terms, but there will be less of them than in the denominator. There will be less than n in the numerator. Okay? And so the zeros are in the numerator, the poles are in the denominator. Now, if you think about what's happening, by the way, if you if you maybe want to plot some of this, you can think here are poles along the real axis, and here might be zeros out here. This is just fictitious, but it's a way of plotting them in the imaginary plane. Okay, and um, so what we're looking at then is we know from fractional decomposition we can always come up with something like this, right? All the terms. And so if the degree of the numerator exceeds that of the denominator, then there will always be a remainder. There will always be a remainder, and you will not be able to meet the condition of converging on a finite result as time approaches infinity. Okay, the second thing that has to be true is that all of the zeros, so here we've taken and done the decomposition and now done the inverse Laplace, and all of the poles must have real parts that are negative. Okay, we like to think of this as all of the poles have to lie in the left-hand plane. Well, that's kind of intuitively, obvious, I think. Here are what those terms all look like, right? With K1s, K2s, Kns. This is if we have unique poles. If we have multiple poles, you get some, t times e to the minus pt. All right, but if this pole lies over here in the right-hand plane, right? If this pole lies over here, oh, come on. If this pole lies over here, right, and this is kind of a conjugate pair here, but if this pole lies over here, the real part is positive. What happens to this? This has a positive on it. And what happens to an e to the positive, right? The time response is going to be like this. If this is time and this is h, right? So that is not going to converge to a finite value. So a circuit is stable when all of the poles of the transfer function lie in the left-hand plane. And this is something you can detect by observation. Okay? So we can look at a circuit we're well familiar with, right? The resonance circuit. And if we do our math on it again, and we're taking the voltage across the capacitor, we know, because we've done this several times, the transfer function is, this is a voltage divider. So here, of course, is the Z of the capacitor. And then this is all equal to Z total, right? The sum of the Z's. All right. So that is our transfer function. And if we go on and manipulate it some, as we're so used to clarify, in other words, separate out the s squared, we get this. We've gone through these equations before. We find that the poles lie at something of this type, minus alpha plus and minus the square root of alpha squared minus omega squared. Okay, now the thing you notice here is what? This value is always less than alpha, right? If omega 0 was 0, the square root of alpha squared would be alpha, and you'd have minus alpha plus alpha, you'd get 0 at least. But this always reduces the alpha squared term so that this will always be less than alpha. And that is why the circuit works and it doesn't run away. Okay, you can just look at the discriminant here. That's the part under the square root. sign and look and see if the square root of that is ever bigger than this, right? In this case, alpha is r over 2l, and omega 0 is 1 over LC. We've done all this before. Okay, and you can, as long as you set numbers that make this true, you're in good shape. All right. So in fact, we can have a case here. If we simply say that r is 0, right? If this is 0, then alpha equals 0. LC can still be something, right? So we get the square root, right? You get the square root of minus something, right? And that's this case, the plus and minus j omega 0. So if you plot those two, what have you got? They're a pole here and the complex or the conjugate pole down there. All right, what is this? Well, without the resistance to dampen things, this configuration is an oscillator, right? That's an unstable condition, but it's one that we like. Okay, so not all unstable things are bad. It's just, is it stable or not? This also gives us some clue since r equals 0, and I said, why does that make it stable? Well, because r is a damping element, right? It takes the energy and converts it to heat. So that's why it would always converge. But as soon as I take that away, it becomes unstable. So it's a good unstable circuit. All right. So one problem here then to follow on with the issue of stability, let's just take a look at, because this is fairly common to have to come down with a transfer function and decide where stability is. So we're going to look at the denominator and find the roots of the denominator. So these will be the poles. And as we just learned, we want the poles to be always in the left-hand plane. In other words, we want the real part of the pole to be negative. So let's just quickly get this. We got minus b, well, that's 25 plus alpha, minus b plus and minus the square root of b squared, whoops, minus 4ac, so times 25. And I'm going to write it like this, all over 2a, which is just 2, right? So this is going to equal, if I pull the 2 up top, I will have minus 25 plus alpha over 2, plus and minus the square root of 25 plus alpha over 2 squared minus 4 over 2 squared is minus 25. Okay, so those are our roots. And now what we're really concerned about is what's going to make this thing either disappear, so there's no real part, in which case we'll have oscillation. So oscillation occurs, where is this, at the real part equals 0, and stability is when the real part is negative. Okay, so we're really just going to watch what's happening here with this. So when the real part is 0, we have this will take place what? When alpha is equal to minus 25. I think that's pretty straightforward. All right, the stability will be an issue when, let's see, alpha, let's just test a couple of values. At alpha, we know it's around minus 25. So at alpha equal minus 24, what would we have? We would have 25 minus 24 is 1, over 2 then. So it would still be minus. So as long as alpha is greater than minus 25, but let's test this. At alpha equals minus 26, we would have what? 25 minus 26 is equal to minus 1. But then this is preceded by a minus sign, so this will end up a plus 1/2, and that will be in the right-hand plane. Okay, so we're going to say then that this is what causes oscillation. Alpha needs to be greater than minus 25 for stability. Okay, and often you have to do with transfer functions, you have to do a stability. You want to know what's stable, what's unstable, and what's oscillatory, especially stability. I mean, often you build a circuit or you build a system, and oops, to my surprise, it's unstable. You can go back through the transfer function and find out what are the conditions that caused instability. And did I meet the unstable conditions with my choice of RLs and Cs or whatever the elements are and the network is? Okay, so this will conclude chapter 16.